Anticipating that you experience that dull opening, would you attend another? In the universe, there is currently a relationship between quantum processing and glaring flaws in this instructive field. In this video, we look at a crucial and shocking discovery made by the James Webb Space Telescope. Inside a dim opening, a telescope, sensed by none other than Bill Nye, the science guy, reveals something incredible. Without a doubt, even light cannot escape from it. Its immense gravitational pull illuminates the mysteries of dim openings, which have puzzled specialists for a long time. However, as of right now, due to unexpected boundaries, we've observed something truly stunning. Despite their size, dim openings consume what could be. As opposed to 1 Earth per day, the shaky but persuasive initial image prepares us for the dim opening in space. Prepare yourself as we begin to explore the incredible nuances of this infinite exposure and its potential implications for stars. At the completion of their life cycle, stars much greater and more enormous than the Sun run out of gas and begin to fail. As they are squashed by gravity, dim openings are formed. It's fascinating to recall how difficult it was to locate the first one, despite the fact that Einstein's relativity hypothesis anticipated their existence. Dim openings of stellar origin emit no light by themselves. They expand and rotate, and these are the only quantifiable properties we have visual verification of. The confirmation of their existence has only recently emerged. For a long time, there was no authoritative endorsement of dim openings. The first observed dim opening, Sagittarius X1, was detected in 1964. However, it took more than 30 years for experts like Kip Thorne and Stephen Hawking to reach a consensus on whether X1 was indeed a dim opening. This discovery was significant in validating their research, but they exercised caution due to the lack of definitive revelations. Hawking and Thorne were almost 100% sure that Sagittarius X1 was a dim opening by 1975, when they made a wager for the first time. By 1988, they were 95% sure. Still, they waited until 1990 to accept verification, when further observations provided satisfactory confirmation. The discovery of Sagittarius X1 was made using 2 spaceborne Geiger counters on a suborbital rocket. These detected a signal directed toward a system 7,200 light-years away. The system consisted of a massive blue star encircling another massive object that emitted powerful X-rays, which made sense if the object were a dim opening. Since its discovery, Sagittarius X1 has been studied extensively. It is multiple times the mass of the Sun, making it the largest known stellar mass dim opening at the time of its discovery. This challenges previous ideas about dim opening formation and the mass loss of stars over time. Sagittarius X1 holds additional records. It has a remarkable mass and the fastest spin speed of any observed dim opening, moving toward the speed of light. This discovery opposes previous assumptions about dim opening development. Recently, it has become evident that dim openings are scattered throughout the universe. Scientists anticipate eventually unraveling their mysteries. While Sagittarius X1 was the first of its kind, countless others continue to be found in surprising locations within 2,000 light-years of Earth. For instance, specialists have discovered a dormant giant in the Milky Way, Gaia BH3, which is the largest stellar mass dim opening in our galaxy. Its mass is several times greater than that of our Sun. Despite being the second closest known dim opening to Earth, Gaia BH3 remained obscure until recently. It was discovered by accident when European space researchers analyzed data from the Gaia mission, which maps our galaxy in 3D. Gaia BH3 is unusual because it is a dormant dim opening that does not actively siphon energy and material from a companion star. This was a complete surprise to astronomers. In the Milky Way, stellar mass dim openings typically have masses several times that of the Sun. Sagittarius X1, for example, holds the record at 15 times the Sun's mass. However, Gaia BH3, with its 33 solar masses, is still small compared to other dim openings, such as the supermassive one at our galaxy's center, Sagittarius A*, which is 4 million times the Sun's mass. Gaia BH3 is Earth's second closest dim opening, with only Gaia BH1, which is 1,500 light-years away, being closer. This discovery provides additional evidence to help cosmologists understand how stellar mass dim openings form. It is believed that massive stars with lower concentrations of heavy metals contribute to the formation of these enormous dim openings. These metal-poor stars, primarily composed of helium and hydrogen, experience slower mass loss, allowing more material to form large dim openings when they collapse and die. Using the James Webb Space Telescope, specialists have discovered an extremely red, massive dim opening existing in the early universe's shadows. Approximately 700 million years after the Big Bang, this massive dim opening took on a reddish hue. The light approaching us is redshifted, suggesting that a thick layer of gas and dust surrounds it. Benan's AV curve and Lucas P. Finnell from NASA's cosmology group analyzed JWST data, determining that this dim opening has around 40 times the Sun's mass. This discovery is significant because it demonstrates that enormous dim openings rapidly consume gas and dust in their surroundings. Located 12.9 billion light-years away, this quasar was initially identified due to its red appearance. Quasars with a red hue occur when massive dim openings are surrounded by large amounts of material, forming an accretion disk of gas and dust. The immense gravitational pull in this situation generates extreme heat, making the quasar shine brightly. The light produced by quasars can be so intense that it outshines all the stars in their host galaxy. The identification of this enormous dim opening was facilitated by gravitational lensing, a phenomenon predicted by Einstein in 1915. According to general relativity, massive objects warp the fabric of spacetime, which results in gravity. The greater the object's mass, the more curvature it induces in spacetime. This effect allowed astronomers to identify and study this distant dim opening in greater detail. The role of gravitational lensing in discovering distant dim openings. Gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity, plays a crucial role in uncovering distant dim openings. When a massive object, such as a galaxy or cluster of galaxies, lies between Earth and a more distant object, it bends and magnifies the light from the background source. This allows astronomers to observe extremely faint or faraway objects that would otherwise be impossible to detect. In the case of the newly discovered massive dim opening, gravitational lensing has provided scientists with unprecedented insights into its structure, surroundings, and growth rate. The lensing effect magnified the dim opening's light, revealing intricate details about its accretion disk and the surrounding gas cloud. This discovery challenges previous assumptions about how quickly dim openings can grow in the early universe. Understanding the evolution of dim openings. The presence of such an enormous dim opening only 700 million years after the Big Bang suggests that dim openings may form and grow much faster than previously thought. Traditional models of dim opening formation propose that they originate from the collapse of massive stars and gradually accumulate mass over billions of years. However, the discovery of this early, supermassive dim opening indicates that alternative formation mechanisms may be at play. One possibility is that these early dim openings formed from the direct collapse of massive gas clouds, bypassing the usual stellar evolution process. Another theory suggests that smaller dim openings merged rapidly in the early universe, leading to their accelerated growth. Scientists are now using advanced simulations and additional JWST observations to test these hypotheses. The impact of dim openings on galaxy formation. Dim openings are not just passive entities consuming surrounding matter, they play a crucial role in shaping galaxies. As they accrete gas and dust, they release immense amounts of energy in the form of radiation and powerful jets. These outflows can influence star formation, either by triggering new star births or by heating and dispersing gas, preventing further star formation. The newly discovered dim opening's redshifted light and surrounding gas cloud suggest that it is in an active feeding phase, consuming matter at an extraordinary rate. This process likely influenced the formation and evolution of its host galaxy, possibly regulating the number of stars that could form in its vicinity. The future of dim opening research. With technological advancements like the James Webb Space Telescope, researchers are now able to study dim openings in greater detail than ever before. Future observations aim to detect even earlier dim openings, shedding light on how they influenced the first galaxies. Additionally, upcoming space missions, such as the European Space Agency's Athena X-ray Observatory and the Laser Interferometer Space Antenna, LISA, will help scientists study dim openings through X-ray emissions and gravitational waves. As we continue to explore the vast universe, the study of dim openings remains one of the most exciting frontiers in astrophysics. These cosmic giants, once thought to be purely theoretical, are now known to be fundamental components of the cosmos, shaping the evolution of galaxies and potentially holding clues to the nature of space and time itself. The bending caused by the light from the stars as it travels near large objects is known as gravitational lensing. This phenomenon lets us see things further away that would otherwise be invisible. This effect was used by JWST and supported by the SMXJ group of the galaxy 7233 to 7327 to amplify the brightness of distant galaxies and reveal the red quasar. This new information adds to the growing body of evidence that the early universe was inhabited by extremely large, dim openings that can range from millions to billions of times heavier than the Sun. Since this phenomenon has been noticed in a variety of large, dim openings in the early universe, It sheds light on the evolution of both the dim opening and the host galaxy, as well as the relationship between the two. However, the typical chicken or egg issue remains on a cosmic scale. Neither the universe nor the dim opening was resolved as coming first. How large were the first dim openings, and how did they evolve? Analysts may have discovered evidence that tiny openings, called microquasars, consuming companion stars, are enormous accelerators for particles that produce high-energy, unidentified galactic radiation that hits Earth. These giant dim openings consume material near a pair of very massive star systems, and a portion of the matter is ejected as relativistic jets moving at unimaginable speeds. Microquasars are the smaller counterparts to quasars. Both are energized by very dim openings consuming nearby matter. In 1912, high-energy particles were found to hit Earth with energies reaching 10 squared electron volts, significantly more active than particles accelerated in the largest helium collider in the world, a powerful atom smasher. According to theory, dimly lit large openings and microquasars are among the most extreme particle accelerators. However, evidence of microquasars accelerating particles to such high velocities has only recently been verified through the High-Energy Stereoscopic System, HESS. Analysts identified exceptionally high-energy gamma rays from the jets of the Milky Way's most powerful microquasar, establishing a link between cosmic rays and microquasars. The microquasar SS433 produces high-energy gamma rays through the interaction of its jets with surrounding matter, creating a shock front that accelerates electrons. These gamma rays travel at such high speeds that SS433 was the first microquasar ever discovered. It is located at the center of the W50 supernova remnant, affectionately referred to as the Manatee Cloud. SS433 has been the focus of extensive research for decades. The system consists of a massive star and a dim opening approximately 10 to 15 times the mass of the Sun. They orbit each other every 13 Earth days, with the dim opening stripping away the outer layers of the star. Some of this material forms an accretion disk, while other parts are ejected as jets traveling at 26% of the speed of light. These jets twist in a thin pattern, forming the W50 supernova remnant and giving it the appearance of a giant manatee. The jets fade over time but return in a recurring pattern, driven by the periodic motion of SS433. The jets from the dim opening also interact with nearby objects, resulting in intricate interactions between the dim opening and its environment. This behavior makes SS433 one of the most fascinating and enlightening objects in the study of microquasars and cosmic particle acceleration. Despite SS433 being the first discovered microquasar, many questions remain regarding how dim openings accelerate particles to such powerful energies and their broader impact on the universe. Scientists study these phenomena using various methods, including indirect measurements. For example, dim openings can be monitored by their interactions with matter and nearby stars, as evidenced by the dramatic increase in X-ray emissions when material is pulled into their gravitational grasp. Understanding dim openings is essential to comprehending the universe. Their study provides fundamental insights into the evolution and behavior of these mysterious objects. In the field of dim opening research, the recent discovery of the most distant known dim opening, a remarkable 13.1 billion light-years away, has significantly improved our understanding. This discovery, made possible by the James Webb Space Telescope, JWST, reveals an exceptionally massive dim opening formed less than a billion years after the Big Bang. This early development challenges existing theories about dim opening formation and galaxy evolution. Evidence suggests that early dim openings played a significant role in shaping the structure of the universe by influencing the formation and development of the earliest galaxies. Dim openings have also been linked to a powerful cosmic phenomenon known as active galactic nuclei, AGN. AGNs are characterized by incredibly bright outflows from the areas surrounding supermassive dim openings at the centers of galaxies. This outflow occurs when material from the accretion disk heats up as it spirals inward, emitting X-rays and other forms of radiation. Studying AGNs provides valuable insights into the feeding behavior of dim openings and their influence on the galaxies they inhabit. Research has shown that AGNs significantly impact galaxy evolution by regulating star formation and distributing heavy elements throughout the galaxy. Advancements in gravitational wave astronomy have also made it possible to examine the characteristics of dim openings. The detection of gravitational waves from merging dim openings, as observed by LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo, has opened a new frontier in understanding these elusive objects. The ability to detect gravitational waves has revolutionized our understanding of dim openings and their role in the universe. These waves, caused by the merging of supermassive dim openings, provide direct evidence of some of the most energetic cosmic events. By analyzing these signals, scientists can determine the masses, spins, and distances of dim openings, offering new insights into their formation and evolution. One of the most exciting discoveries in gravitational wave astronomy is the detection of intermediate mass dim openings. These dim openings, with masses between stellar mass and supermassive dim openings, had long been theorized but were difficult to observe. Their detection suggests a possible evolutionary pathway for dim openings, where smaller dim openings merge over time to form the colossal supermassive dim openings at the centers of galaxies. Furthermore, the study of gravitational waves has provided new perspectives on the early universe. Some theories propose that primordial dim openings formed shortly after the Big Bang, seeding the growth of galaxies. If true, these ancient dim openings could have played a crucial role in shaping the cosmic landscape, influencing everything from star formation to the distribution of matter across the universe. The role of dim openings in galaxy evolution. Dim openings are not just cosmic anomalies, they are fundamental to the evolution of galaxies. Observations suggest that almost every large galaxy, including the Milky Way, hosts a supermassive dim opening at its core. These immense objects, millions to billions of times the mass of the Sun, regulate the behavior of their host galaxies through a process known as feedback. When a supermassive dim opening actively consumes matter, it releases enormous amounts of energy in the form of radiation and high-speed winds. This energy can either trigger star formation or suppress it, depending on the surrounding conditions. In some cases, powerful outflows from the dim opening can blow away gas, preventing new stars from forming and shaping the galaxy's structure over billions of years. Recent observations from JWST and other telescopes suggest that some of the earliest galaxies were shaped by interactions with their central dim openings. The discovery of ancient, highly luminous quasars, powered by supermassive dim openings, indicates that these objects were already influencing their surroundings when the universe was just a fraction of its current age. The mystery of dark matter and dim openings. Another intriguing area of research is the connection between dim openings and dark matter. While dim openings are made of ordinary matter, some scientists speculate that interactions between dim openings and dark matter could reveal clues about the nature of this mysterious substance. One hypothesis suggests that dim openings could serve as laboratories for studying dark matter particles. If dark matter interacts with gravity in unexpected ways, dim openings might warp spacetime differently than expected. Future gravitational wave experiments and high-energy particle detectors could help test these theories. Future missions and the next frontiers. As technology advances, new space missions and observatories are being developed to study dim openings in even greater detail. Some of the most anticipated projects include LISA, Laser Interferometer Space Antenna, a future space-based gravitational wave observatory that will detect low-frequency gravitational waves, allowing scientists to observe mergers of supermassive dim openings across the universe. The Event Horizon Telescope, EHT, building on its groundbreaking image of the M87 dim opening, the EHT continues to refine its ability to directly observe event horizons, the mysterious boundaries beyond which nothing can escape. NASA's Lynx X-ray Observatory, designed to study X-ray emissions from dim openings and other cosmic phenomena, Lynx will provide unprecedented detail on how dim openings interact with their environments. Conclusion: a universe shaped by dim openings. The study of dim openings has transformed our understanding of the universe. From their role in galaxy formation to their ability to accelerate particles to unimaginable speeds, these objects are at the heart of many of the most profound cosmic mysteries. With new telescopes and advanced observational techniques, scientists are now closer than ever to unlocking the secrets of dim openings, and, in doing so, uncovering the fundamental forces that have shaped our universe since the dawn of time.